So I'm flipping over to that online textbook, the How to Think Like a Computer Scientist, one that we looked at the turtles with. So in chapter 1, it's a chapter called The Way of the Program. It's kind of covering some of the same stuff that we've covered in our text. So the Python programming language, what is it? It's a high-level language, meaning that it's written in an English-like syntax with algebraic expressions. A is equal to A plus C and stuff like that. And there are others like C++, Pascal, C, Sharp, and Java. So there are also low-level languages. Those are the machine languages or the assembly languages. Programs that are written in a high-level language have to be translated into something more suitable before they run. They have to be translated into a low-level language before the computer can understand it. So what translates Python is called the Python interpreter. There are two ways to run Python, the immediate mode and the script mode. The immediate mode is just what happens if you type in idle and you get the shell. That's immediate mode. So you can type A is equal to 3 and then you can hit enter, enter, and it'll display 3. So we could actually write Python programs, and some people have done this by mistake when I said to do file new and you skip that step. But the problem is if you make a single typo, you can't correct it. You have to type in the whole thing again. So not so good. But you really could. You could do an import turtle, Alex is equal to turtle dot turtle. You could draw or write an entire program right from immediate mode. Now I don't even see where it drew it. There he is. Okay, so that does work, but we always want to do file new because we always want to run our programs in script mode. Just because we'd like to be able to store our programs and run them later or run them over and over or make mistakes, correct the mistakes in them. So there are different scripting editors you can use. One that this person suggests is called PyScripter. We also have PyCharm available to us on these machines, but the last time I tried to have us pop it open and run with it, it wasn't as successful as I wanted, so I haven't introduced that again this semester. So what is a program? It's a sequence of instructions. Generally, they're concerned with things like input, which is where the user provides some data, get data from the keyboard or a file. Output, it's where you display data to the screen or send it to a file or to some other device. And then math, you can perform your basic mathematical operations. Then there's conditional executions. Conditional executions are like if statements. If A is equal to 3, print hello, that kind of thing. Or the while loops that we've seen. Those are also conditional statements. If this condition exists, do something. If the condition does not exist, don't do it. And then repetition, which is looping. Perform some action repeatedly, usually with some kind of variation. It's going to change a little bit each time, or it's going to be updating a variable or something like that. So debugging. Debugging is the art of finding the problems in your code and fixing them. The first thing that you'll see is just the syntax errors. You type your code in, you find the syntax errors because the program won't run when you do file run. And then you have to type those. And those are usually things like a misspelled variable name, or you left off a colon, or you tabbed something over too far or not enough, or some basic mistake in the syntax and the grammar. But then there are other kinds of problems. There's something called a runtime error and a semantic error. The semantic error is what our other textbook calls a logic error. I'm just going to go ahead and pop open a notepad. So syntax errors, runtime errors, and logic, parentheses, semantic errors. We know what a syntax error is. You made a typo, something like that. A runtime error is when the program hits a state that it cannot recover from. For example, it's trying to save to a file but the disk is full. Or it's supposed to be opening a file but that file does not exist. Or it can't get onto the internet. That kind of thing. Those are all runtime errors. What's the program supposed to do if it can't access the internet? Well, you sure have seen the browser just sit there with a spinning wheel forever, until you close the program. That's maybe not the best way to handle it. Or, if the program can't save to the file because you ejected the flash drive or whatever, what's it supposed to do? Is it just supposed to crash, kill your program? Or is it supposed to pop up an error message saying, could not save to file, pick new file, something like that. So handling runtime errors is your responsibility. Without adding extra code to your program, your runtime errors are going to crash the program. I shouldn't say your runtime errors. It's not you who ran out of disk space. But for example, the simplest runtime error to cause is just divide by 0. So I did a file new, and I don't care if you type this along, but I'm going to do A is equal to B. No, A is equal to 3, B is equal to 0, print A divided by B. Then I'm going to run that. Alrighty, 0 division error. Divide by 0. Problem with that is that dividing by 0 is essentially an undefined mathematical thing. So you have 1 pi and you're going to divide it up amongst 0 people. That doesn't make any sense. So people have come up with a lot of memes or whatever making fun of that. Whoops. Sorry for the language. Okay. Anyways. Great. Just great. You divided by 0, didn't you? Yeah. So on. So you're not supposed to let your program do that. So you divided by 0, let this be a lesson to you. You got to check for that. And how do you check for that? Your program should check to make sure that what the user typed in wasn't a 0. Or if you're trying to calculate the average, that you're not saying, okay, the average was this many points over 0 tests. Whatever. There are some things that you can do to handle runtime errors programmatically. I could have put an if b not equal to 0, colon, print A divided by B, else, colon, print cannot divide by 0. That solves that runtime error. Okay, so at least it didn't blow up with red text. And if this was in the part of a larger program, you would have the user re-enter the data that they needed to enter, or you'd perform some other calculation to make sure that that value was non-zero. So runtime errors are things like file not found, disk full, divide by 0, and there are plenty of others. And syntax errors are things like grammar mistakes and typo, and we understand grammar to mean just where you put your semicolons, and your colons and stuff like that. And then logic errors are when the program runs but produces the wrong output due to bad logic. You type in 10 pounds, and it's supposed to be translating it to kilograms, and it says 10 pounds is equal to 10 kilograms. Well, it didn't crash, it just didn't give you a good answer. So a lot of debugging. The syntax errors are pretty easy to spot. Maybe not at first, but the program just doesn't run. And so once it runs, you know that you're out of syntax errors. But logic errors are harder to find. You have to actually dig through your code and figure out why those 10 pounds equal 10 kilograms. What the mistake was. And I think I did something like that in here. Or I did some division and then I printed out the wrong thing. And then the runtime errors are the unexpected ones that you just have to plan ahead for. And then whenever you see one come up, then you write, some code that would handle it. Now, we're not going to spend too much time on figuring out how to handle things like file not found and stuff like that. But we'll do a little of that. So experimental debugging. Let's see if I can crank this text up. Experimental debugging, it's like detective work. You're confronted with clues. The clue is that we entered 10 pounds and it printed out 10 kilograms. So we have to infer the processes and events that led to the results you see. Well, the first thing we have to validate is that the user actually typed in 10 pounds. Users will sometimes claim that they did everything right and yet it gave them the wrong answer. But if you sit down with them and then watch them do it again, they'll do the wrong thing. And so maybe you need to make the instructions in the program a little bit clearer or whatever. It's also an experimental science. You modify your program and you run it again. If your hypothesis was correct, you can predict the result of the modification and you're a step closer to solving the problem. So if I get really stuck and I'm working with y'all on something, sometimes what I'll do is, I'll add some print statements. We'll print out the weight at an intermediate point and we'll print out the kilograms at a slightly later point, trying to figure out what's going on, how that number is changing and where at. So you can add print statements to your code to figure out, the intermediate states of the program to figure out what's going wrong with the process. As Sherlock Holmes pointed out, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. Alrighty. So for some people, programming and debugging are the same thing. The programming is a process of gradually debugging a program until it does what you want. The idea is that you start with a program that does something, and then you start making small modifications. And you keep it a running program, a working program all the way as you go. For example, Linux is an operating system kernel that contains millions of lines of code, but it started out as a simple program that Linus Torvalds used to explore the 386 chip. His earliest project was something that would display AAAA on the screen and then would change the letters BBBB. So, wow, he started off small, but because he just wanted to learn how to program the chip, without using an operating system like Windows or something like that. Then it grew into this thing that, is used, by the millions today. Hopefully by now we know what the pound signs mean, the hashtags. If I say comment out a line of code, that just means put a pound sign in front of it. Like if I say comment out that A is equal to 3, then you should come up and do that. That's what I mean. Comment out that B is equal to 0. Okay, you should do that. Now that we've done that, the rest of the program is broken because it's trying to refer to variables that have not been created. Exception is another name for a runtime error. The program generated an exception. Now they're talking all, computer sciencey talk. So if you're doing a divide by 0, in some languages, some some programming environments will call that a runtime exception. I don't remember if this one does. Let's undo my changes, run it again, and see if that's the language that it uses. You will certainly see that term if you go on to become a C or a Java programmer. Oh, well, since it's accommodating, excuse me, since it's accommodating the error, then I can't see the result of it because we actually skirted our way around the error by good programming. Okay, it's not calling it an exception here, but so I'm going to kind of throw away that term. Okay, I'm going to switch back to the PowerPoint. We were talking about modules. The idea behind modules is abstraction. We want to be able to draw a square with a single call, just so that we can put square parentheses in parentheses, or so that we can do square and then pass in a number and we'll draw a square of that size. That lets the person who uses our library of code to pay, or you yourself later, pay attention to the important stuff while ignoring the non-essential details. You know, somebody else who comes in and wants to figure out how to use your turtle program doesn't need to know how the square is being drawn. They just need to know that if they use that word square followed by the parentheses, it'll draw a square. One important thing about modularization is it allows multiple programmers to work on a problem. I could say, okay, I want you to do the square problem, but I want you to draw an octagon, and I want you to draw, you know, a half circle. And then each one of you could write a module that did that. And then we could chain those together to go ahead and draw our picture that we were trying to go for. So rarely does a single programmer write a commercial program. Usually you have teams. Professional software developers can write new programs quickly by dividing the programs up into modules, and you assign each module to an individual programmer or a team. Modularization allows you to reuse work. If I ever wanted to draw squares with turtles again, I could go and find that program that we wrote last week, and just use that. So it's reusable. Allows individual modules to be used in a variety of applications, and that's good, you know, because if you can use code that has been written before, then, you know, you've already gotten a lot of your job done. You can show that the video game programmers reuse code from their last project an awful lot, or they, you know, they rent or acquire the rights to a graphics engine that somebody else has, you know, has made a game with, so that you can then do the same. And reliability. Reliability is incredibly important because you don't want your programs to crash in the user's hands. So very quickly uninstall it, you know, after the second time it does that. And if the modules in your code have all been tested individually, then you can be a lot surer that when the program runs together, that the program is going to work. And then if something goes wrong, you know where to zero in. Oh, my triangle code has got the wrong angle, so it's not drawing triangles, it's drawing U-shapes. So when you write a modular program, you have a main program. And then you have modules. The main program is the code down, let me see if I can open up the code that we did on Friday. Wednesday, excuse me. Alrighty. So in Python, the main program is all the stuff that's unindented, or that starts with the unindented lines. Now we set everything up with a Leo's equal to turtle call and an import turtle call and some stuff like that. I'm going to modify this code like that. But then we defined all of our modules. And then we had some calls to our modules, and then we defined some more modules, and then we had some more calls to our, you know. That's not really a very well-structured program, but we were making it up as we went along, and I didn't want to scroll up and down too much, so that's the way I did it. What we should try to do, here's the way that a program should be structured in this language, is that all the modules should be defined up at the top. You know, and there should be a comment block up above that, you know, name, date, whatever. And so then anything that needs to set up those modules, like import statements and maybe a couple of, you know, object creations, turtle creation, and, you know, the screen creation, all that stuff goes up at the top. But then after that, all your modules come. And then and only then does the main part of your program come. So this is the main code. The main code is the stuff that, you know, in our pseudocode is between the start and the stop. So if we had wanted to make this look like pseudocode, we could put a start there. We could put a stop there. And you certainly don't have to modify Wednesday's code to look like this. But that's the idea. The main code is the code that's unindented. The modules are the things that you define above them. Each module, which I promised I was going to start calling a function, but the textbook calls a module so exclusively that I start doing it. The function definition, this is the function header, where you use the def keyword, you give the function a name, and then if the argument is supposed to accept, if the function is supposed to accept any values, like, you know, a number between the parentheses, you have to add a variable between the parentheses to accept that value. This value here, 100, that's called the argument, and SL is called the parameter. The variable that gets filled in is the parameter. So in general, modules go above main, program. Main program is the unindented code. There'll be indentions inside the main program, right, once you hit if statements or loops or whatever, but it's the stuff that starts off unindented. Each module, parentheses function, begins with a, what are they calling it here? A module header. The DEF statement, like this, DEF, triangle, parentheses, side length. So DEF is the keyword that starts the header. You always have to have it. And then triangle is the name of the function. And then SL is the parameter. You can have a whole bunch of parameters if you want. We only needed one, right, to draw this triangle, but we could have made it so that you could pass in a color for the triangle, in which case we would have, that way each triangle we drew. Some people played with that. Some people wanted the triangles to be in different colors. But to do that with our code wasn't super easy, right? You had to draw a triangle, you had to set a color here, and then you had to set another color there, and then you had to set another color there. But we could have made it where you would say, okay, I want a triangle that's got a side length of 30, and I want this one to be red. And I want a triangle that's got a side length of 60, and I want this one to be blue, right? But then it's got two arguments here. Arguments are the values when you invoke the function. Parameters are the values that accept it. So up here, we would have written triangle so that not only did it accept a side length parameter, it also accepted a second one, for example, color. And then we could change the name of the turtle to that color before we drew the triangle. Guess I could demonstrate that just to show you all that it actually works. Alright, so I have these lines of code here. This triangle is going to be 30 with red, this triangle is going to be 60 blue, and this triangle is going to be 90 and it's going to be green. Let's give that a shot and actually see if, well, I didn't actually change the color, but I made a small change. I want to make sure it doesn't crash yet. Alright, well, it's not going to work because I didn't actually make it change the color, so they're still all going to be yellow. But since we have the parameter called color, we could change Leo to that color before he starts drawing. I'll do that. Leo.color, parentheses, color. I could give this a different name so that it doesn't look so funny, because that repeated word looks a little bit weird. But doesn't really matter. Calling it color here makes it real obvious that that's what we're supposed to be passing in, so I'm going to leave it. Alright, so now when it draws the triangles, they'll each one be a different color. That makes this function more flexible. We could also make it so that you pass in a parameter that says if it's supposed to be hollow or filled. We could make it so that it changes the pin length. Maybe we want to make it so that different triangles are drawn at different speeds, so you could pass in a speed. That one sounds a little bit more dubious to me. So the module consists of a header and a body and then a return statement. In our language and in many languages, the return statement is implied. What does that mean? I don't have to have a return here for it to actually get out of the triangle method. Why is that? Because the first time it hits an unindented line of code, it treats that as a return statement. Why does it do that? To make Python easier to write, so you don't have to stick on an extra sentence that's not necessary. But if it was going to return a value, like it was going to calculate the square root of something, you would need a return statement to return that value out of it. And when we pseudocode these things, we are going to put the line return down at the bottom of them. So it wouldn't be a bad idea, and I kind of waffle on this, so I'm putting return at the end of every one of my functions. Because it sure does make obvious where the function stops, right? But it's also pretty obvious that the function has stopped by that time. So, I don't know. Let's go ahead and put our notes there. You know, function has a def, a name, a parameter list, which could be empty. That's the stuff between the parentheses. And then it has a body of code, which is all indented. And then it's got a return statement, which in Python can often be left out. So let's list these like a bullet point. The function has a header, which consists of those things. It's got a body of code, and then it's got a return statement. All right, that ought to be pretty clear. Anybody ever go back and look at the notes? Some of y'all lie and wave your hands just to make me feel good. No, I'm kidding. Yeah, thanks. All righty. I did see a few hands. That makes me feel good. Okay. So naming a module is like naming a variable. Same rules. You can use letters, numbers, and underscores with no spaces, and it has to start with a letter. So when the main program wants to use a function, it calls the module's name, just like we called the triangle function down here, right? We called square. The techie term for that is invoking. When you call, parentheses, invoke, a function, you use the function's name and provide arguments to fill in the parameters, if any. If you think back to Wednesday, our first version of the triangle or the square didn't take any parameters. You just said square, and it drew a square of the same size every time. But then we modified it so that it had a parameter, so we had to pass in a size argument each time. And the arguments go inside the parentheses. So example, square 100. Square is the function name, 100 is the argument. So modularizing a program. You can break a program up like this. Well, what you do is when you start writing your program, you try to break it up mentally. Even if you didn't pseudocode it to begin with, you can think, okay, I'm going to have an input section, I'm going to have some output section, I'm going to have a calculation section. Well, what order do I need to do that? Input, calculate, output. Then later on, or even from the beginning, you can try to think of those things in terms of modules. Now I want to go ahead and demonstrate flowcharting a module or modules. So go ahead and pop open Lucidchart and log in. Hey, neat. They have a tablet version if you want to bring in your Samsung or iPad or something like that and draw flowcharts that way. I can't imagine drawing flowcharts on a phone, although phones are pretty big nowadays. Alright, it keeps giving me an error. I'm going to try logging in with the... Oh, because I'm typing in the wrong thing. That would be why. Typed in my D2L password. Okay. So we've seen flowcharts. We've done a couple of them. Don't draw what I'm about to draw because I'm just going to modify a current one right now. Move my name over. But this is how you flowchart a module. It starts at another terminator, but it doesn't use the word start. And then it ends with another terminator, but it doesn't use the word stop. Instead, it has the word return. And then it has some code between it. Blah, 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 do stuff. So, whatever the process is, right? It could be, one line of code. That'd be kind of dumb. Why make it a module if it's one line of code? It could be 1,000 lines of code. Now, when you want to invoke it, the module, you use a different symbol. It looks like the math block. It looks like the process block. But instead, it's got the vertical bars, like somebody's military ribbons or something. Predefined process. And like I said, we're going to go to one that actually draws that. So, triangle, like that. I'm going to go ahead and put the parentheses at the end of the DEF here. Also going to see if I can increase the size of the font. Can I do that? There we go. Right, okay. So now looking at this. The way the program runs is that this is the main code. Kind of wish that it just had the word main rather than start, but okay. We know that start in a flowchart or pseudocode is the same as the main code in our program. And some programming languages actually require you to put the word main in your program to indicate where it starts. Not this one. So it does some stuff, it gets some input, it inputs some height, and then it calls our triangle function. So imagine this is some kind of teleport, like Star Trek, they're teleporting to the surface of the planet. It runs over here, it runs all this code, and then beam me up, Scotty, it goes back here, it finishes. But we don't draw those lines, they're implied by the fact that we have a process call here. And if we wanted to do baby steps, we could show, we could draw a line, from here to here and here to here and make them dotted lines or something like that. But no, we're not going to do that. We're smart and educated enough to know that if you have a process block, which is the one with the vertical bars, I think the textbook shows them with horizontal bars, same thing. Then it hops up over there, does all that stuff, and then it comes back. So we're not going to be drawing those lines. You just have to think of those lines. You have to understand that that's the way that it works. Now a module can call another module. I could have another module here that calls a third one, a second one. I don't know what to call it, so I'm going to call it what. And then I could go over here and I could add a what module. DEF what, right? And then it could do some stuff, whatever it's supposed to do, and then it could do a return. Like that. So when the code was running, triangle, whoops, okay, that's a process block, so we're going to jump over and run the function. It runs and starts running triangle. It does some stuff, and then, oops, here's another function call. Runs over here, runs all that code, then returns back to there, so that then it returns back from there. Excuse me. Okay, so what would this print out? Wrong answer. It's going to print A, B, C, D. Well, C and A and a B and a C and a D, so that's what I'm going to put on my exam. Oh, but that wouldn't get you credit. What is it really going to print? What's the first thing that it does? What does it print first? Yeah, it prints an A. Then what happens? Does it print B? No, it runs over here. So it prints C. So it's going to print A, C, then it comes over here, and it prints D. I should have made it print A, C, D, C. Anyways, and then return, comes back here, returns, and then it prints the B. So it print A, C, D, B.
Is that a what or wood?
It's what misspelled completely. W-H-U-T. Sorry. I should have given it a better name, like Fred and Barney, something like that. It's certainly not a triangle anymore.
Just want to make sure it's not a command.
Yeah, yeah. All right, I'm going to undo all that, and then we're going to draw a flowchart that kind of resembles the code that we did on Wednesday. So I'm going to make a new one. File, new document. And so they all begin, all the main functions start with a terminator that says start. Main programs, excuse me. Now the textbook shows having a block of declarations. Why would you do that? So that if you had like a is equal to 0, pi is equal to 3.14, weight is equal to 32, you know, if you had a whole bunch of list of variables, it would be really annoying if you had to list each one in a separate math block, right? So instead, you just put one block for your declarations. Now we had a few declarations. We imported the turtle, and we created the screen and the turtle. So import turtle. Well, that didn't work. Import turtle. And then to get to the next line, I should have been hitting control, return, create Leo turtle, create win screen. Something like that. Maybe the opposite order. Don't remember how we did it in the code. Well, I guess I could stop being lazy and actually go look. Okay, we created the windows first. I'm going to try to rearrange that. Cut the create win screen. Put that before the create turtle line. And it looks kind of ugly having the text all centered. In the textbook, they had the word declarations, I believe, up at the top, declarations like that, and then they had stuff indented underneath it. I don't care so much about that. If we wanted to make it look just like the book, though, declarations, colon, control enter. There, those are our declarations. If I wanted them to be aligned to the left, I could double click on the entire line of text and then use this little center icon up here that says align to the left. Whatever. I don't want you to take time during an exam aligning stuff. I mean, you could be going on and doing the next part of the, this exam. I'm not going to have you draw a lot of flowcharts, but it'd be fair to ask for one flowchart during an exam. But not a hugely complicated one. That would chew up too much time. Okay, so there we go. If we go back and we look at our code, after our declarations, there were some definitions. Now, you don't put the definitions in line with your main code in the flowchart. Instead, we look for the unindented stuff, and we drew 3 squares. That was our code. So I'm going to add function calls to draw 3 squares, or at least 1. So I drew an arrow down, and I added a predefined process block, which is going to call square, whatever square function we define, with a size of 100. That block's a little tall. I'm going to shrink it down. You don't have to. All right, now if we were going to also do a triangle function, we might want to call the triangle function. So I'm going to add one more process block that calls triangle. All right, there's our work so far. And I always spend more time formatting than you need to, but that's, for one thing, that's to give people time to catch up. All righty. And then at the end of our program, our main program, what do we need at the bottom? Just like we did on our pseudocode, what's the last line in a pseudocode? Stop, yeah. Return is for modules, for functions. So stop. And just as a reminder, the words start and stop do not actually occur in our Python code. They're just there in these charts. Just like if you're building a house and the blueprints have, length measurements, 10.5 feet or whatever, the 10.5 is not part of the things that you're putting down. It's just showing you how to build it. Okay. Now we need to define a square module. So we need another oval, another terminator, and we're going to call this square, but to indicate that it's a function, I like to add the word def. It makes it look too much like Python, but whatever. And then the name of it is square, and then we need to pass in a side length. Why am I calling it SL? Because typing side length takes longer. That's the only reason. If I was writing this program for myself or for publication or to give to somebody, I'd actually put in the whole word side length. So if we go back and look at our code, what if I don't remember what our square code looked like? I would go and I would find our definition of a square. I'm going to leave out the comments, but I see some lines of code. Side is equal to 1, and then a while loop. Now I haven't shown you all how to flowchart a while loop, so this is chart wandering off the plot into new territory, but that's okay. So I'm going to draw a line down here, use a math block to assign a variable called side and give it a value of 1. And then underneath that, I'm going to use a decision symbol. It's the same symbol we use for if statements. While side is less than or equal to 4. Now the textbook would leave off the word while. I will post a PowerPoint showing my preferred ways of flowcharting. I don't care if you do it the way the textbook does it. I don't care if you do it the way I do it. I would prefer you do it the way I do it. The problem with doing it that way is that there's some variance between what you're reading in one place and what you're reading somewhere else. Just keep in mind that there's always more than one way of doing things, and my way is valid and the book's way is valid. Okay, so that's our decision block. And if this is true, we're going to jut off to the right, draw a line, and then turn. So it's almost too much, too Pythonese to actually put the command that tells them to draw the line forward side length. Draw side length line, or forward side length line. Or just forward side length. How about that? Then we're going to come down here and we're going to turn our turtle to the left or to the right. I forget which way we did it in the text. In our program, I'm going to go look. We turn left. Not that it matters, right? Left 90 degrees. Then we need to add one to side, because if side always remained 1, then this while loop would always be less than or equal to 4, and it would never stop drawing the square. So then side equals side plus 1. Pseudocode would add the word set in front of it. Getting kind of tired of that side window popping up every time I do something. Okay. And then it needs to go back up to the while block. See if you can get it to go to the side. Like that. If you can't, at least hook it back up, like that. But it's cooler if it hits one of the diagonal sides. I don't want it to hit the bottom because that's where the other line that leaves the while block is going to come from. All right, and then once the drawing of it is done, we return. I think that's enough illustrations of drawing triangles. Of drawing stuff. So I'm going to delete this triangle call down here. I don't feel like doing a triangle module. So I'm going to delete that one from over here in the main code. Delete one of the arrows and stretch the other one appropriately. Okay. So that's code for drawing a triangle. Square. That is a flowchart for drawing a square. Is it perfect? Not really. It's missing a few things, but gives you the idea. And really that's all a flowchart has to do, is give you the idea. I could have skipped the declarations entirely and just trusted that you would be able to do the rest. What am I leaving out? For one thing, I'm leaving out the word that the turtle is named Leo over here. But I didn't really just want to type leo.forward, which is, too Pythonese. But there wouldn't be anything wrong with that. And then leo.left. Oh, it's not 09 degrees, it's 90. Hello, dyslexia. There we go. Alrighty. So, that'd be okay. I think I'm going to go ahead and leave it like that. And then I want to wander around and make sure y'all are doing good. If you were going to draw a decision block, remember that code that I did that said if b is equal to 0, print an error message, else divide by 0, or, do your division. I want to do another little block of code that does something like that. Since it's going to be in the middle of code, I'm not going to actually do a whole start and stop. I guess I could. Why not? Okay. So this is another main code. This is the program that we did this morning, that I did this morning. it had some declarations up at the top. So I'm going to put a declaration block up at the top. Declarations. A is equal to 3, B is equal to 0. That's kind of a dumb program. We should be asking the user for those values, but I'm making this as short as possible. That wasn't the point of that particular line of code. The point of that code was to illustrate a runtime error. But then we had a statement, if I go back and look, if B is not equal to 0, do something, else do something. The if is a decision block. So, if, I'm going to make it say if B is equal to 0 rather than not 0, and I'm just going to flip the logic in my mind. I'm going to print the error message first. Or is my true option. My brain works better when I think of terms of positives, not negative. Right? Like if you start speaking English and you use doubles and triple negatives in your sentences, you know, it is not unwelcome. It takes longer to parse that as being it is welcome. So anyways, so if B is equal to 0, we need to print our error message. Output cannot divide by 0. But if that's not the case, we want to actually divide by 0. And I didn't leave enough room, so I'm drawing this one with an elbow like that. I could take the time to make it all match if I so wanted. Here we go, like that. And so this would be output A divided by 3. Then they need to hook back together. The way I like to hook them back together was with a little circle called a connector. When you drag a circle out, it has a letter in it, but we don't need that letter. So I'm going to remove the circle. I'm going to try to make the circle small. You don't have to do that. All right, and then at that point, the program was done. So I'm just going to put a stop at the bottom of it. Okay, that's the way a decision block looks if it's not a while. Again, the textbook would leave off the word if. The textbook will leave the word while off, I believe. So if I wanted to make this textbook perfect, I would delete that word if. I think it's easier to understand myself. So I would leave that word there because that kind of looks like an assignment. Yeah, you know it's a decision because it's in a diamond. But, you know, we have space to put the while. We have space to put the word if. Why not do it? So you see the difference between the if and the while? The if branches off two ways, but keeps going. The while branches off two ways, but one of the ways goes and repeats some code. I'm going to show you one more thing the book does that I disagree with, which is that this final line out of the while loop goes up to the top like that. I really need to drag this stuff over. Like that. It works. You want to draw it like that? That'd be okay. Maybe I ought to start doing that. Yeah, I'm going to start doing that. I'm going to start doing that. You don't have to change your flowchart to match, but if you want to, you could delete that line that does that and make it do that instead. That's cool. I'll abide by the book. I've been broken. They beat me. Okay. Now, in your code, or when you're saying these things, people say, if, then, else. That's the way they say it. There is no then word in this programming language, though. And there's not even a then word in our pseudocode, really. If we go and look at our code and we try to match it with that, here's what the code looks like for that. You know, we could add a start and a stop at the bottom to make it look closer, more similar. But you see what I'm saying? There's no then word, even though that's what I would say. I'll try not to say it because you don't type in then, but if b is not equal to 0, print, else print. Now when we're drawing over here, people kind of wish that there was an else word, because every line of code's got to have a, you know, an equivalent block. So if they want to drag an else block over, they may, you know, don't do this. This is wrong. I'm going to stick the word else here or something like that because it was in my program. No, a decision block does not have an else. It's implied. Right. So this is the then implied. This is the else implied. In the past, I have played with teaching students to put no/else or just else here. But I'm going to try to go a little bit more by the book. So just remember, if you see the code structured this way, you're going to indent this code after the if block, but then you're going to indent this code as well, but after the word else. Alrighty. Autograph time. So what I'm going to do for y'all is I'm going to give y'all a flowchart that I want you to turn into Python code. And at this point, I don't even care if the Python code works. I just want to see the words if, you know, and the calculations, you know, and the word else and stuff like that. It doesn't have to follow the syntax exactly. So in effect, it's pseudocode. So if you wanted to do it in pseudocode, that would be fine as well. But I'm going to give you a flowchart, and I want you to turn it into code, either Python code or pseudocode. And it's more awesome if you actually get it to be working Python. But it's okay if you don't. It's going to be a simple program, you know, no more than 10 lines of code. So I will upload that. I don't want to show it to you now. Some people start working on the homework the second I upload it. I got to draw it, really. So that's why I'm not giving it to you now. Maybe I will. Why don't we just draw it? We have a little bit more time. So start. Input temperature. Then we're going to do a conversion. Then we're going to call an if statement. If C is less than 0, we're going to print freezing. Otherwise, we're going to output not freezing. That's going to be our little joining connector. That doesn't have an actual line of code that corresponds with it. And then we're just going to print a done message and then our stop. Now I'm drawing it more quickly than I'm expecting people to actually key it in because I'm going to give you the flowchart. What am I missing from this flowchart? If I wanted to give you absolutely everything, there's something I'm missing. And it's not in this column. I'm missing an entire block of code. What block of code am I going to need to add? I don't have a convert module. I'm calling it, but I don't have it. So I would also draw def convert f. Then I would convert it with a math. C is equal to f minus 32 times 5 divided by 9. I believe that's the right equation. And then return C. Give that a shot. Turn it into either pseudocode or Python code. If we look at the text, there should be Python code, excuse me, there should be pseudocode for defining modules. Don't tell me there's not. Fine, be that way. Alrighty, so if we were going to try, I'm going to leave it like that, and then we're going to go back in and we're going to do an example or two more on Wednesday. Because I don't feel like you have quite enough information on how to do pseudocode. You actually do have enough information to do Python if I publish all the notes that we've done, which I will. All right, let's make a Dropbox. So you're going to want to export. You're going to want to do a download as on your file. So do a file, save. I guess it didn't ask for a name. I guess I had to do a save as to actually give it a name. So I'm going to call this modules, parentheses functions. You can call it whatever you want. February 19. Then I need to actually download it because I can't upload it until I download it. So file, download as. PDF is a great format. Surprised Word doc isn't there. Oh, well, anyways. And then pick a good place to save it. And that'll be what you upload. So let's make a Dropbox for it.